So in this question, we are given that let G be a group with the property that for any xyz in G, we have xy is equal to zx implies that y is equal to z. Okay. Now we have to prove that G is abelian. Okay. So we have that G is a group and G has a property. What is the property? It is that xy is equal to zx. This will imply that y is equal to z. Okay, this is the special property that the group G has. Okay, we are asked to prove that G is abelian. All right, so to prove G is abelian. Okay, now by definition, when do we say that a group G is abelian? We say that a group G is abelian if the operation is commutative, right? That is, for any say a comma b in G, we have AB must be equal to BA. Okay, if we can show that for any a comma b in G, AB is equal to BA, that is, this commutes, then we say that group G is abelian. All right, so somehow we have to use this given property and show that commutativity exists. All right, okay, so let's begin with okay, let a comma b be in G. Okay, random, arbitrarily I am taking a comma b in G. Okay, we'll have that AB equal to AB, no doubt. Okay, now somehow we have to bring in this property. So what is the motivation? So let me show some rough work. So we have to show that AB equal to BA, right? We know that G is a group and A for any element A inverse will exist and we can multiply on both sides by A inverse, right? So we'll have that AB A inverse will be equal to B. Okay, if we somehow show that this is true, AB A inverse is equal to B, then we are done, right? Then if AB A inverse is equal to B, then again by multiplying on both sides by A, we will get this AB is equal to BA, right? So this is our motivation. We have to show that AB A inverse is equal to B. Okay, so somehow if we introduce this A inverse, etc., then we have a way to go about it, right? So what I will do is I'll just take a manipulation, that is I will write this AB uh, into operated with identity. Okay, here E stands for the identity in the group. Okay, so we know that on doing the operation with identity there is no change. So AB times E is same as AB itself, right? So I will write this as E. Now, why did I write this as E? We know that A inverse into A is equal to E. So using this E, we can introduce this A inverse term, right? So I will write this as AB A inverse. Okay, one second. Let me be precise. So okay, so I will write this as AB into A inverse A. All right. So what do we have now? We have that AB is actually equal to AB into A inverse. All right. Now, by associativity, okay, we have that AB A inverse into A. Okay, by associativity. So here we see that the axioms of the group, whatever is there in the definition, comes into play. Right. Here we used the existence of identity, existence of inverse, and now here we are also using associativity. So each axiom in the definition is very important. Okay. Okay, now what do we have? So we have A into B is actually equal to ABA inverse into A. Now look at this. We have A on the left, A on the right. What is the given property? Given property is that if we have X in the left and X in the right, we can actually cancel this and we will get that Y is equal to Z, right? So using the property, what do we have? We have A into B is actually equal to ABA inverse. Now this is into A, right? So using the property, given property, we will have this by using the given property. This is where we use the property. Okay, by using given property, we have this. So we have B is actually equal to A inverse. This was our motivation. This is what we started with, right? Now we will multiply on both sides by A and we will get BA. is actually equal to AB. And this is true. So what do we have here? We said that uh, for any a comma b in G, we have AB is equal to BA. But this is precisely the definition of abelianness. So G is abelian. Okay, this is what we wanted to prove.